Today we're going to be talking about exponential growth and decay and separation of variables of differential equations. And the growth and decay is something that you may have seen in pre-calculus, and even I do a little bit of this in my Algebra 2 with trig class, but we're going to put our calculus spin on it. But first I want to start with some examples of solving differential equations by separation of variables. So our first example here. You take your differential equation and you separate the variables, meaning anything that is a y goes with the dy. So I have a y squared dy. Anything that is an x squared, you put with the dx. Any x variable, you put with the dx. And remember, you always want the dy and the dx on the numerator. Now we take our integral, and it's kind of fun, I think, that both of the integrals are the same thing. Don't forget your plus c. Remember on the AP test that this is like, say it's a 6 or 5 point question, you would only get, I think it's like 1 or 2 points if you forget that c. Okay, so that's a huge deal. So at this point, this is when I plug in my initial condition. So I plug in my initial condition of 1/3 of 2 cubed is equal to, when I plug in 0 there, I get c. So my c ends up being 8/3. So I have 1/3 y cubed equals 1/3 x cubed plus 8/3. Multiply everything by 3. And then we take the cube root of both sides. Remember that differential equations, you want to be solving for the y. Second example. Again, remember that this y prime means dy dx. So I separate my variables and I get dy over y is equal to x squared dx. I take the integral of both sides. So when I'm taking the integral of both sides, remember 1 over y is ln of the absolute value of y equals 1/3 x cubed plus c. Now, right here is when you decide, actually, no, we can convert. Yeah. Let's convert this to an exponential. So I am going to write this as e to the 1/3 x to the third plus c is equal to the absolute value of y. Now, at this point, you look at your initial condition. And your initial condition in this case, y is equal to 1 and x is equal to 3. So I have a positive y as my output. So I leave that as y. And then let's talk about this piece here. I kind of glazed over this in the last video, and I want to talk a little bit more about this here. Remember that this really means adding the exponents, same base, you multiply. So really what I have here is I have a new constant. I'm going to call it constant 2, e to the x to the third over 3. So now this is when you plug in your values. 1 equals my constant. I just name it something different because I just want you to recognize that this constant here is different than this constant. You really don't have to, but I'm going to. I had seen that on a few different calculus things that I had been working on. So that is e to the 9th. So our c is equal to e to the negative 9th, or 1 over e to the 9th. I'm just writing as negative 9. So my equation here is e to the negative 9 times by e to the x cubed over 3. Remember, same base, I can add the exponents. So maybe I didn't even have to do this piece where I made my new C. But that's going to be in a lot of the problems that we see, just so that you know. It actually leads us into our next example. Okay, this is, I think, a good application of growth and decay. So a population of a hive of hornets is growing at a rate proportional to the population. So the population is growing at a rate. So I'm growing at a certain rate that is proportional to my population. This is going to get me an exponential equation. So this is the differential equation for an exponential function, in other words. On May 1st, there was 10 hornets. 30 days later, there was 50. When will the population reach 125? So something you need to keep in mind. May 1st, let's call that time 0. There was 10. So I have a point, 0, 10. And then we have a population of 30 days later, there was 50. So 30 days later, there was 50. That's going to be important to us later on. But let's look at this differential equation. Let's separate out our variables. This P needs to go with the dP. So I have dP over P is equal to K dt. I integrate both sides. So I have ln of P is equal to KT plus C e to the KT with my new constant out in front is equal to the absolute value of P. Now I'm talking about my population growing, so P is going to be positive. Hopefully that looks familiar to you guys from exponential growth and decay. Now what we have is if I plug in 10 for my P, I plug in 0, we get C to equal 10. This is the initial condition, okay? Unless in the next example, it's not going to be the initial condition. But in these straightforward examples, that's going to be your initial condition. So I have P equals 10 e to the KT. I need to find, I call this, it's not the correlation coefficient, it's the growth rate, that K. We need to use this other point to find K. So to find K, I plug in 50 for P. Now be careful on this. When I was doing these problems last night, I was screwing this up and I was getting 1/5. Just be careful. Ln of 5 is equal to 30K. So K is equal to the ln of 5 over 30. We're in Calculus BC. This is who this video is designed for. It's also for AB, technically. I want you guys to leave this like that. I don't want you to find the decimal. So we finally have our equation. Our population now I need to find when will the population, so I'm looking for a T, 125 hornets. So 125 is equal to 10 e to the ln of 5 over 30 t. So solving that equation, quite honestly, what I would do, since you guys have calculators, you don't have to solve it algebraically. If this were a question on a test or a quiz, I would just expect you guys to get the answer at this point. I would put this in y2, put that in y1, and find their intersection. So I get t to be 47.0797. I was looking for my units, days. That's what I did. You could solve it algebraically if you want. But I just put one in, I put this in y1, this in y2, and I solved from there. Next example. The rate of change in the number of foxes in a population, I'm going to be using n because the n of t was messing me up when I was doing this, is directly proportional to n, where t is time in years. They give me an initial condition. They give me another point. So they give me an initial condition. They give me another point, which is 3, 500. I need to find when t is equal to 5. So the key here is this first sentence. The rate of change of number of foxes in a population is. So the rate of change, hey, that's a fancy way of saying derivative, is directly proportional to 550 minus n. Okay, solving this differential equation, we separate out our variables. Taking the antiderivative of this, I would make sure you guys do a u substitution because the actual antiderivative is negative ln of that. So make sure that if you need to, stop the video, do your u substitution. Equals kt plus c. I'm going to multiply by a negative 1. Now, the negative just gets absorbed into the c. You have to trust me on that. From here, it's just a matter of negative e to the kt plus my new constant c is equal to 550 minus n. Notice how I took away the absolute value signs, because I forgot to put them in. But the reason that I took away the absolute value signs is no matter what, when I'm plugging in any of these populations, I am getting a positive number here. So I don't have to worry about the populations growing, so I don't have to worry about a negative. And so from here, I'm going to use this initial condition to get my c. So I have c e to the 0 equals 550 minus 250. Because of this 550 minus n, our c is something different than what the initial condition was. So keep that in mind. This is, I'm going to call this a not straightforward differential equation. So now we have this equation. We have 300 e to the negative kt equals 550 minus n. I am going to bring the n over to this side. Now what I'm going to do is I'm going to use this point, and I'm going to find my k, my growth constant. Okay, so from here, I get, so subtracting the 550, dividing by the negative 300, I get 1/6 equals e to the negative k times 3. So solving for k, I get k to be equal to the ln of 1/6 divided by a negative 3. So now I have my n as a function of t function. If I plug in this k into there, that the two negatives cancel each other out, so I get ln of 1/6 over 3t. Now here it is a matter of now just plugging in 5. And they didn't tell me how to round. It's some sort of decimal. It's like 534.6 something. So I'm going to say it's 535 boxes. Okay, so that is your video on separation of variables and growth and decay. So it's 2 sections, but for my BCers, you guys have seen this before, so we can kind of cram it together into one.